class, this podcast has to do with heating curves. And heating curves are really going to combine the two things we've learned about Q and delta H so far. We're going to combine them to make kind of a problem that kind of takes a long time to solve, but it's really pretty straightforward. All right. So heating curves is the topic. And what would happen if we plotted temperature, if we started with a bunch of ice, all right, and just added heat to it gradually and turned it into steam eventually, all right? So what would happen is we would start at a pretty low temperature, and our temperature would increase kind of at a nice pace, and then it would flatten out, all right? We'll talk about that in a second. And it's going to increase for a while, and then it's going to flatten out for a long time, and then it's going to go up. All right, so if we plotted that, if we just had time on the bottom and just kind of added consistent, steady heat, so we have time down here, and then over here is going to be degrees Celsius, let's say. So it's going to be temperature. So there's two temperatures if we're talking about water, and water is the only heating curve we're going to talk about in general chemistry. But there's two temperatures that always happen, and they always happen at the same spots. All right, so something happens at 0 degrees, and another thing happens at 100 degrees. Okay? And if it's less than 0, we have ice all the time. If it's greater than 100, we have steam all the time. And if the temperature is between 0 and 100, we have liquid water. All right? So where we have slanty areas, all right, so there, and there, all right, so these three sections, we're going to use this equation, Q equals MC delta T, which is an equation we've seen, we've used it, and you're familiar with that. All right? However, at these two spots where it's flat, all right, delta T doesn't work for us anymore because the change in temperature is 0. So for these two spots, we use delta H equals M H, and it's either going to be fuse or vap. Fuse, remember, is when we are melting things, and vap is when we are boiling things. So you might just add fuse and vap, but it's the same equation, delta H equals MH. So anyways, that is really what we're learning, all right? So what's going to happen is, if we just label these sections on our graph, let's just label them 1, 2, 3, 4, and 5. All right, we're going to see how this is helpful in a second. All right, so if we take this scenario, if you heat 50 grams of ice at negative 15.2 degrees Celsius to steam at 198 degrees Celsius, how many calories are required? So what happens on these problems is probably the best thing to do is, we always know these two numbers are going to be there, 0 and 100. However, in this case, we're going to add two more values. We're going to add negative 15.2. We're going to also add, way up here, 198 degrees Celsius. Right? And now what's going to happen is we're going to simply make 5 little mathematical equations and label them 1, 2, 3, 4, 5. And then we're going to get the answer to each of them and then add them up, and that's going to be the total amount of energy required to heat ice to this amount of steam. All right. So, for the first one, because we have a slanty line, we're going to use Q equals MC delta T. So M is 50 grams, and then the specific heat of ice is 0.51 calories per gram. Or per gram degrees Celsius. And then our temperature change is, it stops being ice at 0 degrees. So we're going to take 0 minus negative 15.2. All right? So we're really going to add those, and then our answer is going to be 387.6 calories. All right, so the next part of the equation is going to be delta H equals MH fuse. So we're going to take mass, which is going to always be 50 for this particular problem. We're going to multiply by the heat of fusion of water, which is 80.87 calories per gram. And the answer to that is 4,043.5 calories. All right, the next thing is we need to heat our water, because we now melted our ice to liquid water. So we're back to Q equals MC delta T. So we have 50 grams of water now. And because we're talking about water, the specific heat is going to change. So it's not the specific heat of ice anymore, but it's the specific heat of water, which is 1 calorie per gram degrees Celsius. And then our temperature change is, it stops being water at 100, and it starts being water at 0. It's just the difference of those two. And really, if we take 50 times 100 times 1, we get 5,000 calories. Alright, next part is step 4, which is going to be delta H equals mH vap now. So we have 50 grams, and then the heat of vaporization of water is 547 calories per gram. And just so you know, all these values, these constants, I'll give you the specific heat of ice, the specific heat of steam, delta H or delta heat of vaporization of water, heat of fusion of water. You just need to know what to do with these and when to use them. Alright, the answer to this is 27,360 calories. Alright, then the last thing we have to do is just heat up our steam. Alright, so we're back to a slanty line. And slanties are Q equals MC delta T. So we're going to have M, which is 50 grams yet again, times C this time, which is the specific heat of steam, which is 0.48 calories per gram degrees Celsius. And then lastly, our final temperature is we're heating the steam to 198 degrees, but it starts being steam at 100 degrees. So the difference of that is 98. So we get an answer of 2,352 calories. Alright, and our last step is simply adding all these up. Alright? And notice they're all positive. If we are adding heat, it's obviously going to be endothermic because that thing is absorbing the heat, so everything is going to be positive. What happens if we are doing a cooling curve? If we do a cooling curve, all of our values should be negative, and we're going to have a really, really big negative value, because if it's cooling, it's being exothermic, or just giving off heat if it is cooling itself. Alright? So again, we're going to add all these up, and our final answer is 34,341.1 calories. Alright? And as far as significant figures go, obviously on each of these when we multiply, we should probably be rounding to 3 significant figures or around there. So what I would do is if I just look at my problem that I begin with, so up here, everything had 3 sig figs to start with. So probably a good rule of thumb would just be, we could probably round this to 34,300 calories. And that would be pretty accurate, alright? But really, I'm mainly concerned that you're doing the math correctly and setting everything up. Alright, the one thing that could change on homework and even on quizzes is, let's say instead of starting at negative 15.2 degrees Celsius, we start at 30 degrees Celsius. So if we just did this real quick and did a map, alright, so we might just, by default, put 100 and 0. But now I'm saying, let's say we start at 34 degrees Celsius, so we start with water, and we're going to warm water up, we're going to boil water, and then we're going to heat the water, alright, or heat the steam. So if we did something like this, alright, and just changed our original question, instead of starting at negative 15.2 but 34, notice how many sections does this graph now have? It has 1, 2, 3 sections. What's really going to happen is we can ignore the first and second steps that we did in our problem over here, because we're already starting with liquid water. So because we're already starting with liquid water, or since we're already starting with liquid instead of with ice, we can ignore those first 2 things because we don't have to melt the ice, we don't have to heat the ice. So problems could be easier than this, but the worst problems will always have 5 steps. And that is it.